Okay, hello everyone. Welcome to today's lecture. Last in last lecture, our like last hours, you had midterm exam. I hope it went well for everyone. I also uploaded the solution for that exam and made an announcement. So if you want, you can go ahead and you can check that solution and find out whether your answers were correct or not, right? I have asked TA to grade the exam, and hopefully next week, the grades for the midterm two exam will be released, and then you will have an option or opportunity to have a look at your uh, graded exams. Okay, so before the exam, we were talking about CPU scheduling, our process scheduling algorithms, and finally we were able to complete that part. So today we are going to start a new topic, which is about process synchronization. So uh, I'm directly going to the main slide. So the first question is why we need the process synchronization, or what does it mean to synchronize processes, right? So what happens if there is no mechanism for synchronizing the execution of two or more processes? First thing is that you need process synchronization only when two or more processes they are sharing some resources. Like for example, if they are sharing the data or they are sharing files, they are sharing any kind of entity, right? If they are accessing share if they are sorry, they are sharing access to an entity data item, so their accesses to that shared item need to be synchronized. Why? Because if we do not synchronize their accesses, then the shared item or the shared data end up in a inconsistent state, right? We will see an example and then it will become clear to you how that thing can happen, right? So concurrent access to the shared data, it can result in data inconsistency, and therefore, if we want to maintain our data or shared data structures in a consistent state, we need to ensure that all the accesses by different processes to that shared data item are performed in a synchronized way. And as I said, that shared item can be anything. It can be a shared memory variable, it can be a file, it can be a global variable in a multi-threaded program, it can be a kernel variable or a kernel data structure. So remember, in one of previous lectures, we talked about producer-consumer problem, right? In context of process communication, right? So we try to revisit that example again. The last time when we had a look at the producer-consumer problem, we implemented it through a shared buffer. But our implementation had a limitation, if you remember. So if, for example, the size of our queue or buffer was, let's say, 10 elements, which mean it can at a time, it has the capacity to store 10 items. So we said that we will be using only 9 out of those 10 slots. So one slot was kept always empty, right? So there was no issue in terms of consistency of the data, the messages, or the queue itself. But the downside was that we were wasting one slot, or we were keeping one slot empty all the time. Now let's say we don't want to do that. We don't want to waste that slot, right? So this time what we are doing is that we maintain an integer counter which actually keeps the count of how many items are placed in the queue, right? So this count variable is now also a shared variable. So between producer and consumer, they both have access not only to the shared buffer or queue, they also have access to the shared variable count. And what happens is the following. Whenever producer produces a new item and places it in the queue, it increases the counter variable to tell, like, okay, for example, there are now currently 10 elements or items available in the queue, right? And on the other side, what does the consumer do is the following. After retrieving an item, it decrements the counter to indicate the current total number of items available in the queue, right? And again, both buffer and the count variable both are shared between producer and the consumer. Now, the thing is like when our producer and consumer they are accessing the queue and the count variable separately mean like let's say first producer fills all the items or it fills the buffer with to the maximum capacity and then it waits for the consumer and then consumer reads all the items and it empties the queue, then there is no problem in the sense we don't have any data consistency issues. However, that is now how the things work in real life. We don't have we will there is no point of then having uh, uh, queue if we say that okay producer will always first fill the queue and then consumer will always first empty the queue before producer can put any more elements, right? So it can be possible that at any given time both producer is trying to put an element in the queue and consumer is trying to extract or retrieve an element from the queue, right? So if that is the case, then we end up having a problem. What is that problem? Before going before discussing that, let's have a look at the pseudocode of the producer and the consumer. So on the producer side, what we have that when it produces an item, it puts a link or a pointer to that item in the next produced variable or pointer, and then it checks is the what is the value of the count. If count is equal to buffer size, it's mean that the queue is full. So if queue is full, then our producer will wait. It will do nothing. It will wait until count is not equal to buffer anymore, which mean that it waits for the consumer to retrieve an element and to reduce the value of the count, right? So when the count is not equal to buffer size anymore, then our producer will go ahead and what it will do is that it will produce. Remember from the previous example, previous our previous discussion of producer and consumer, we were also maintaining in and out indexes, right? So it will then place the next produced element in the queue at the index in, and it will increment the in by one, and then it will also increment the count to indicate the total number of items, right? On the other hand, what consumer is doing that it first checks if count is equal to 0, which means that there is no element in the queue. If there is no element in the queue, it has nothing to read, right? Or nothing to retrieve. So it will wait. So when the value becomes greater than 0, which means that the producer has placed at least one element in the queue, then consumer can go ahead. It will read a new element out from the queue and store it locally and then increase the out index. uh, and at the same time it reduces the count, right? And after that it consumes the item. So this is the pseudocode for producer and the consumer, right? But we haven't yet discussed what is the data consistency problem we inconsistency problem we face. So to understand that problem, assume that we initially have five items in the queue or the buffer, right? And then assume that producer has just produced a new item. So we are going to take a snapshot in time, like at a particular time point during the execution of the producer and the consumer. And at that particular point, we have currently five items in the queue. Producer has just produced a new item and it want to put it into the buffer and it has already placed it in the buffer and is about to increment the count. It has not yet incremented the count, but it is about to increment the count. At the same time, remember producer and we are assuming producer and consumer, they are running on two separate cores at that same time, right? Now, assume that the consumer has just retrieved an item from the buffer and it is about to decrement the account, right? So that is like point in time we are discussing. It means that producer and consumer both producer is about to execute count plus plus and consumer is about to execute count minus minus statement, right? So this is what we are talking about. So initially, let's focus on the top half of the figure, right? So initially, at the time point where we are talking about, we have five elements in the queue, and then producer produces a new element and it has placed that element in the queue, and now the next thing it is supposed to do is increment the count variable. And at the same time, consumer has just retrieved an element from the queue, and the next thing it is about to do is decrement the count variable, right? Or it can be like also in another, like here we assume that first producer is putting the element in the queue and then consumer is removing, right? It can also be the other way around. Like initially you have five elements and consumer has retrieved an element from the queue and it is about to decrement the counter, and the producer has placed an element in the queue and it is about to increment the counter, right? So if that is the case, so let's say if I say that first producer, so initially if there, okay, let me go here. So how many elements are there in the queue? Five, right? If now let's say producer goes ahead and place an item and increments the count, so it will become what? The count will become six, right? And then let's say if consumer goes ahead and retrieve an element, reduces the count, so it will become five. So the correct value after both have producer has incremented and consumer has decremented the count, the correct value of the count should be equal to five, right? Even in the second scenario, again, you can do the same thing. Let's say we have initially five items. Consumer first retrieves an element and decrements the counter. So it becomes four. Then producer places a new item in the queue and increments the counter. So it becomes five. So again, when consumer has decremented and producer has incremented, the final value should be equal to 5, right? Because one element is placed, one element is retrieved. So again, the net total sum is again 5. However, here is the problem. The problem is, the part of the problem is that this count plus plus statement, which we have written in higher level language, when you translate it into assembly, it is converted into into multiple instructions. So for example, the first instruction is that you load the data from memory into the register. For example, if you have uh, I don't know if you have taken the assembly language course, so you remember we were doing some instructions. For example, load into register, let's say register R16, the value from memory address X. Instead of X, you can write count. Okay, let me erase it. So you are first loading the value from count into register R16, right? And then you are saying, okay, now increment the register. So like, for example, you have instruction increment R16, and then you are saying, okay, put the value, incremented value from register uh, back into the memory. For example, store, uh, sorry, my mistake. For example, store in the memory location named count the value from register R16, right? And same goes for the decrement operation. When you write, you can write as a single statement in a higher level language, but in assembly it will be translated into three different instructions. Again, first you are loading the value of count into a register, then you are decrementing the register, then you are storing the value from the register back into the memory, right? So the point is that each of these statement is converted into multiple instructions, right? Now, remember again, our producer is about to execute the count plus plus and our consumer is about to execute count minus minus. But the execution is done. Again, what is executed is assembly instructions are executed. So let's say what happens is this, that because they are executing independently, right, on two different cores. So let's say that uh, our producer here in this slide, we have black color for the producer and what is this? This brown color. brown color for consumer, right? So let's say first producer executes the first statement, which is it loads the value from the memory into the register, right? And let's say at that time our consumer was doing something else, right? So like this is interleaving. Interleaving means they are running on two different core. So I can do like this, like you have here, let's say core 0 running producer and core 1 running consumer. And here it runs S0, S1, and at that time consumer was doing something else, right? And then consumer runs S2 and S3, and maybe when consumer is running as step 2 and step 3, producer is context switched with some other process, right? And then it comes back and it runs S4, and when it is running S4, maybe let's say consumer is context switched out by some other process, and then it comes back and it runs S5, right? So now what happens is this one, that count is placed in register 1. So remember, initially count is equal to five. So register 1 is equal to 5. Then register 1 is incremented. So register value becomes 6, not the value of the count in memory. Value of count in memory is still 5, right? But then our producer is, let's say, context switched out here, right? And our consumer is running. And what does it do is that it also loads the value into its register from memory location. So it loads 2 in register 2, it loads 5. And then it's decremented, so it becomes 4. The value in register becomes 4. And then process 4, process producer comes again, and it's execute. It puts the value from register into the memory. So it writes count is equal to 6, right? But again, this is the same memory location which is written by both producer and the consumer. So once the consumer comes back from the after the context switch, so what happens is that it also writes the same value of 4 in the same memory location, right? So we end up having final value of 4 for the count, which is not a legal value. It is not possible. Why it is not possible? Because we said in our example, producer is putting one element and consumer is extracting or retrieving one element with initial number of element was 5. So one added, one removed. So we should have the final number of elements equal to 4, equal to 5. But we end up having 4, right? And if you like switch the order, let's say if consumer executes before producer, so S5 appears in time before S4. So what will happen? The final value of count will become equal to 6, right? So it means that we can possibly have the value of count equal to 4, final value of count equal to 4, or final value of count equal to 6. Or if you have like first, as if you have the order where you have S0 executed, then S1, and then S2, and S0, let me write this, S0, S1, S2, and then S3, S4, and S5, the final value of counter will be equal to 5 in that case, which will be the correct value, right? So I'm not writing that. The final value of the count will be equal to 5. So which means that we will have three possible values depending upon different interleavings. Either the final value will be 4 or 5 or 6. Only 5 is correct. 4 and 6 are incorrect. It means that if you now run this producer consumer program, sometime you will get the correct result and sometime you will get the incorrect result, and it all depends upon how those processes they are scheduled, who gets the turn first to run, and whether their and how their execution is interleaved, right? Is everyone clear on this? What is like how this data inconsistency problem is appearing? So it is appearing basically because of the fact that there are two processes, or or even there can be multiple threads of the same process which are accessing the shared data, but they are not their accesses to the shared data are not controlled, are not synchronized, right? So
Right.
all depends upon the scheduler, who is allowed to first. So if it scheduler ends up having an interleaving which gives the correct result, then you will get the correct result. If scheduler ends up having an interleaving a schedule where the interleaving is not correct, and then you will end up having inconsistent result or inconsistent data. Okay, yeah, someone was saying something and I was not able to stop because I was in the middle of something. Yeah, go ahead if you have a question or comment. No? Okay.
Or I was just saying that that makes sense. Yeah, that both processes run, but like you said, the data isn't synchronized, so we end up with whichever one does it last with the information.
Yeah, that's correct. That's correct. So actually here we have an animation of exactly what we just have seen. So let's say you have CPU and you have producer and consumer, and they both share this variable count, access to the variable count. So let's say if your producer runs first, so it executes the instruction. So producer want to do count plus plus and consumer want to do count minus minus. So but again, when converted into assembly, these statements convert into multiple instruction. So let's say producer is successful in running the first instruction, which is register 1 is equal to count. So in its register, it puts the value of count, which is 5. Then it goes ahead and does the next instruction, and which is increments the value of the register, and it becomes 6, right? But then before it is able to execute the next instruction, let's say it is the context switched out, right? And then and let's say the consumer runs. So consumer reads the value of count into its register 5, and then let's say it also decrements its value, so it becomes 4. Now let's say now consumer is context switched out and producer is allowed to run. So now if the producer runs, it puts the value of the register 1 back into the count. So count becomes 6, right? And if now after that consumer is again allowed to is scheduled for execution, it will update the value of count again in memory, so it will become 4. So which is not the correct value, right? So what is the problem? The problem is like uh, these count plus plus and count minus minus operations, they are divided into multiple instructions. So if we say like the execution of the producer cannot be how to say uh, it cannot be stopped. Like if it has started executing the first instruction, it must complete the last instruction before it can be context switched out. And same goes for the consumer. If it has started executing the first instruction, so it must complete the last one before it can be context switched. If we can place this restriction, then we will end up having the correct result all the time. Okay. So this problem is known as race condition. Race condition happens when two or more processes or two or more threads, they are trying to access the shared data, but since their accesses are not synchronized, so it happens that we end up having inconsistent data as a result of those accesses, and the results which we see, they are not easily reproducible, because the result you will see, it all depends upon the interleaving and ordering, right? So it will be very difficult for you. For example, let's say you wrote a program, you run it and tested it only once, and it showed you correct result, right? And let's say it was a assignment, and then you send me that assignment. I'm evaluating it, and I run it, and when I run it, I saw a different result, which is incorrect, right? Now it will be very difficult for you. You can say, "Oh, I have tested it. I was seeing the correct result." But I will say, "Okay, no. In my case, I am not able to see the correct result, or not all the time." So now it will be very hard for you to debug what is the problem, like from where, what is the source of having incorrect result. So that's why it's always important to synchronize the accesses to share data by multiple processes or threads. So race condition, in this example, we have count values can be 4, 6, or 5 in various runs, but it should be a 5 as a result of one increment and one decrement. Only 5 is the correct value, right? So interleaved access to count variable causes data inconsistency, and such problematic situations are called race conditions. So now we should develop programs that do not have race condition. And how we can do that? How can we avoid the race condition? By implementing process synchronization. And this is big issue because the wrong results we see, they are not easily reproducible, or maybe because there are one thing is like there are multiple wrong results. Like for example, let's say the your program is supposed to output the value of 100, but sometime it is giving you 100, sometime 50, sometime 20, sometime 70. So it will be very difficult for you to understand what is happening. Again, this is just a screenshot from the book. So I just wanted to read out this one. Such a situation like this, just like an example we have seen, where several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access has taken place. This situation is known as race condition. Okay. So in previous example, for consistent result, which is 5, either count plus plus should be executed and finished first, just like I said, it should not be interrupted while it has started the execution, or count minus minus should be executed and finished. They should not be interleaved. So to avoid race condition, we need to enforce non-interleaved access or atomic access to the shared data. And for that, we need synchronization or coordination of thread processes while accessing the shared data. Okay. Now, this takes us to the issue of the critical section. So what is critical section of a program or a process? So critical section of a program or process is the part which is accessing and changing the shared data with the data which is shared with the other processes. For example, here in this figure we have three processes: process one, process two, and three. Process 1 is changing the variable x and y. Process 2 is changing variable x, y, and x. And process 3 is changing variable only y, right? So process 1 and 2, they share x with each other. So it changing the process of the steps to change the x, it makes the critical section from the perspective of process 1 and process 2. So it is the critical section between process 1 and process 2. When you look at the variable which is shared among all three, so this is the critical section among all three processes, 1, 2, and 3. Okay, it's mean that we need to for the variable x, we need to synchronize the accesses between process 1 and 2, and for variable y, we need to synchronize accesses between process 1, 2, and 3. So how we can do that? By dividing our program lifetime and giving it into different section and giving it a structure. So the part of a thread or process that is accessing and manipulating the shared data is called critical section. Just like here we have like changing x is a critical section and changing y is a critical section, right? So we should not allow more than one thread to be in the critical sections at the same time. Only one process, for example, here in the critical section Y, at any given time, only process one of the processes like either 1, 2, or 3, they can change Y, not more than Y, and not more than one process can do that. A thread may also be executing in non-critical section, remainder section, and actually the parallel or concurrent execution of that part is desirable. So for example, if in the context that let's say you have some other operation, process 3 has some other operations here, right? So when let's say process 1 is allowed to enter the critical section change Y, then yes, process 3 cannot do this part like where it is changing, but it can do the other remaining part of its computation or execution, which is not accessing any shared data or any shared item with other processes. And actually it is a desirable feature, and we should allow the remainder section to be executed in parallel with other processes. Okay, so how we can then structure our program to solve the critical section problem. So again, you have two sections, critical section and the remainder section. Critical section is the one which is accessing the data shared by other processes, and remainder section is one which is doing something or accessing some data which is not shared with any other process. So you replace it into with a new version where you have an entry section before the critical section and you have an exit section after the critical section, right? And then the job of this entry section is to control that only one process is able to enter the critical section. So the feature of this entry section is that it implements the restriction that only one process can enter this critical section at any given time. So we will see how we can do that, how we can implement the entry section. But before going to before having a look at that, uh, let's have a look at the features or the requirement for a solution which addresses the critical section problem. So for any solution that addresses the critical section problem, it must have three properties. First, the mutual exclusion, which basically mean that only one process at any given time can enter the critical section. Let me just read this statement. So if process PI is executing in its critical section, then no other process can be executing in their critical section, right? And again, remember, critical section is the section of the code which is accessing a shared data, that data shared among multiple processes. Second, progress, which basically mean that uh, if uh, if there is no process which is executing in the critical section, and there exists some processes who wish to enter the critical section, then then they should be allowed to enter without being postponed indefinitely, which basically mean that no deadlock. So like for example, if let's say as long as there is at least one uh, requester to enter the critical section, then they should be allowed to enter the critical section. Like let's say if there is one, then it will definitely enter the critical section. If there are two, then one of those two will enter the critical section. If there are four, then one of those four will enter the critical section. We don't want to end up a situation where we have, let's say, four requesters processes trying to enter the critical section and none of them are able to enter the critical section, right? If that happens, it is known as a deadlock, and we don't want to have deadlock. Bounded waiting, it's mean that let's say if there are four processes, P1, P2, P3, and P4, and they have a critical section, so it should not be the case that let's say P1, P2, and P3 always get the chance to enter, but P4 is waiting forever. So there should be, yes, there can be waiting, but the waiting seen by or experienced by a process to before it can execute the critical section should be bounded. It should not be infinite, right? Because if that happens, then it means that some processes are starving. Note that this is different from deadlock. In deadlock, what happens is we have we have requesters trying to enter the critical section, but none of them are able to enter the critical section. In starvation, what happens is that we have multiple requesters. Some of them are able to enter the critical section, but there is at least one which is never able to enter the critical section, and it is like waiting forever. And it is that's why it is known as starving. And when we are trying to build a solution for the critical section problem with and that solution is supposed to have all these three features, so in that context, we are assuming that all these processes they execute at a non-zero speed. Non-zero speed mean that mean it takes some time, some latency for those processes to execute. They are not like it's not an ideal world where a process can execute in a 0 minute, a zero time. Second thing, that we are not making any assumptions concerning the relative speed of the processes. So for example, if you have two processes and both are trying to enter the critical section, we are not saying like process A is running at a very high speed, I don't know, because of some reason, so it always succeeds before the process B to enter the critical section. So there we are not making any assumption. It can be like maybe process A and B both are running at the same speed. Maybe process A is slower, process B is slower. we don't know anything about their relative speed. Any questions? Okay. So where is this critical section problem appears, and definitely the venues where we have where we see this problem, we need to apply the solution. So we can face this problem in multiprocess applications which are sharing file or sharing memory segment, because they may try to access the shared file or the memory segment at the same time and end up corrupting the file or the data, or bringing it to inconsistent state. Uh, we can also have this critical section problem in multi-threaded applications, sharing global variables. So we also need to synchronize their accesses. Or this problem can also appear in the kernel itself, because why? Because kernel is actually a multi-threaded software. So there are like multiple kernel threads, kernel level threads, which are implementing the kernel features or the kernel services. So it is quite possible that multiple of those threads, they are trying to access the same kernel data structure at the same time. So if their accesses to the kernel data structures are not synchronized, they can end up corrupting the kernel data structure, or making it inconsistent. Any questions? No? Okay. Peterson solution. We actually have seen this solution earlier, but let's try to have a look at it again, and then now maybe not today, but in the next lecture we'll try to apply this Peterson algorithm to solve the critical section problem, right? Uh, so this solution is for two processes, and it assumes that the load and store instructions are atomic. That is, they cannot be interrupted. So what does it mean? So it means like, let's say this is your memory, and in the memory you have, this is your some particular location, which is, let's say in our context of producer consumer problem, it contains the variable count, right? So load and store instructions are atomic, means, let's say if both producer and consumer, they want to update the count, right? But before updating, they need to bring the count variable into the register, and also which is known as loading. And once they have like uh, incremented the value of the count in the register, they need to write back the new value in the memory. This is known as this is called the store operation, right? So for example, producer will first load the data into the register, right? And once after incrementing, it puts the data back into the memory. This is known as store. Now what we are saying here, that they are atomic, it's mean that this load operation or the load step, it cannot be interrupted by any other one. So once the producer is allowed to initiate the load operation, so no one can access, it cannot be context switched out. So it will be context switched out only once the data is available in the register. After that, yes, maybe scheduler will kick it out, depending upon the scheduling algorithm, right? Similarly, if producer has issued the execute instruction for storing, so before like the completion of the store instruction, producer cannot be kicked out. It can be possibly kicked out only after the completion of the store instruction. Okay, so that is what we mean by being atomic. So in this solution, again, as we said, this is only for two processes. So if you have more than two processes and you want to synchronize their accesses to the critical section, you cannot use the Peterson's algorithm. Maybe some variant or some modified version of the Peterson algorithm, but not the original one. So the two processes, they share two variables, which is turn and interested. So interested is actually an array consisting of two elements, and turn is a single variable. So the variable turn indicates whose turn it is to enter the critical section. So, and the interested array is used to indicate if a process is ready to enter the critical. Ready mean that if a process is interested in entering the critical section, but only showing your interest is not enough. You can enter in the critical section only if the other process is not interested, or if the other process is interested but it is not his turn, right? So if that is the case, only then you can enter the critical section. So this is how your algorithm for like from the perspective of process, single process looks like. So let's say you have a process pi. So what it will do is that, remember, we have the shared array interested, right? I'm writing only intr to indicate that, and it has two elements, 0 and 1. So let's say I is equal to 0. So it first publishes its interest by setting interest I equal to true. So let's say I'm writing here t is equal to 0, and then it sets turn equal to j, which is it is giving the turn to the which is like equivalent of saying that it wants to give turn to the other process, not to itself first. So it is just trying to be polite, right? So it says, okay, it's your turn, not my turn, right? So then it checks, okay, while interested j and turn. So here it is checking if the other process is interested and it is if it is the turn of the other process and that other process is also interested, then do nothing, wait, right? So in the same time, remember that the other process will also be running at the same time. So which takes us to the next slide, right? So here you have like both versions again. So this is your interested array. So 0, 1, both publish their interest by putting true in their respective elements of the interest array. But then turn is a single variable, right? So it is also shared turn. It is also shared, but it is a single variable, right? So both of them try to write at the same place. Let's say if this goes first, goes first mean, because remember we said that load and store are atomic. So let's say process 0 gets the chance to write the value in the variable turn. So it will write 1 here, right? And then it will reach here and will see, okay, J is interested. The process 1 is interested and it is the turn of the J. So it will not go ahead. It will be start looping. But then when process J comes in and its right turn is equal to I, so it's our write this equal to 0, right? Now what will happen, that this condition will not be true anymore and this can enter the critical section. But at the same time, this will not be able to enter the critical section because why? Because I, which is 0, is interested and turn is equal to 0. Remember, the final value of turn is equal to 0. So it will process, this process will be waiting and process 0 will continue running and it will enter the critical section. Once it enter the critical, it is done with the critical section, then it will say, I am not interested anymore. So it is right, like putting here false. So when it puts false here, so what will happen, that this second process which was looping at this point, for this second process, this first part of the condition becomes false because now interested 0 is not true anymore, it is false. So it will be able to enter the critical section, right? And then after it will go back and it will again, the both of them will again publish their interest if they want to enter the critical section again. Any questions? Okay, so I have prepared this small animation just to make it clear that how things are working in the Peterson algorithm. So let's say you have two processes. I'm naming them blue and purple one. So let's say the blue says, okay, I'm interested. Purple says also I'm interested. But then blue one says, okay, I need to be polite. So it gives a coin which indicates the turn to the purple one, right? But then the purple says that, yeah, I'm interested, but I also need to be polite. So it gives the coin back, right? So it is like, what is important? Who finally gets the coin? Like it is equivalent of who writes the final value to the turn in our algorithm, right? So now the blue says, okay, she is interested but has no coin. So remember what was the condition? That if the other process is interested and it is the other process turns, then I must wait. Here, what is happening? Yeah, the other process is interested, but the other process has no coin. So I can start execution, right? And the purple one finds that yes, the other process is interested and has coin, so I must wait. But blue one, yeah, she's interested but has no coin, so I can start execution. So then this blue process starts executing, and once done, it says, Okay, I'm done, not interested anymore." So if it is not interested anymore, so the purple one sees that he has coin, yes, but he is not interested anymore, right? So if it is not he's not interested anymore, I can start execution. So then this purple will start execution, and once completed, then both of them will like again they can go back to the point where they again publish their interest. Okay. So we are finishing today a bit earlier. I think maybe I should have prepared some more slides, but I haven't. I don't know. I mean, I was thinking I'm going slow, so there is no point of like preparing too many slides.
Extra, right?
So, yeah, I need to time myself maybe. Uh, okay, so do you have any questions at this point?
And there was a no quiz today because of the midterm.
Yeah, there is no quiz, but we have
Okay.
time. If you want, we can go ahead and we can actually try to, if there is there anyone who want me to share the solution of the exam? No one? I hope everyone then had a good exam. I mean, the and average is high. Okay. It seems no one feels the need to discuss the solution. Anyway,
Uh,
yeah.
I
It
guess
shows
real
that there
quick.
is a quiz. There is a quiz. Yeah, go ahead. Go ahead.
I was just gonna say real quick, can I get like a brief reminder on the round robins? Because was it, I know it was set into 10-second or 10 time increments. And then did we cycle to whichever one was added most recently? I'll admit, I got an answer for that one, but I think I got that one wrong.
Okay. Okay, I will get back to that like oh, sorry. But someone said that there is a quiz scheduled today. Let me check if that is the case. Today is 11. Today is quiz. Okay. Okay, let me check. Okay, let me stop sharing the screen and see if the quiz is ready or not because I was thinking, I'm sorry for that. I was thinking like there is no quiz today. Let me check if the quiz is prepared and available. Yeah, yeah, quiz
Yeah, I'm
9.
seeing quiz 9 is currently
Yeah,
set.
it is not released yet. It will be released in some time. Yeah, so yeah, you guys have quiz today. So don't forget to take the quiz. Okay, then I can start. Uh, Thank you for reminding us that we have the quiz. So then I can start sharing the. Okay, so you want it. You have some comment and confusion on question 4?
Yeah, I also realized I could just look at the answer myself, but so let's
Yeah,
see.
so here the Gantt chart is there. I mean,
All right, A. No, that's more or less what I did, if I remember right. Okay.
yeah. So, and I don't know it was this question or the other one. I think in question 3, yeah, there were some cases where you have two processes with the same remaining time. So that's why I placed this restriction that if two processes have same remaining time, you can schedule the one which appears first in the alphabetical order.
All
Like,
right, that one made more sense to me. It was round robin. I was struggling to remember.
yeah, okay. Okay, so it seems like everyone is fine with with me not discussing the solution. If that is the case, then that's all for now. If you don't have any questions, then I'm going to end the meeting. And yeah, see you next week.
Thank you.
Thank you.